So I'll now move on to probabilistic reachability for MDPs. Okay, so I'll first give you an introduction, then I'll consider the case of qualitative probabilistic reachability. So this is, can I reach a target with probability greater than 0? I'll then introduce the optimality equations for probabilistic reachability, and then I'll give you 3 different approaches for computing reachability probabilities. So first, as we saw for our DTMC's, probabilistic reachability is the fundamental concept in quantitative verification, and it concerns the probability of reaching some target set. So if we've got a strategy sigma and a starting state S, then we can consider what's the probability of reaching the target under the strategy sigma when starting from the state S. And I'll use this annotation here. So this is similar as for our DTMCs, but we need to specify the strategy first to resolve the non-determinism. So if we consider a MDP, well, we've got a set of possible strategies. So we can do the best or worst case analysis. So this is the lower or upper bounds based over all strategies. So we can either consider the minimum probability of reaching the target starting from state S. So here we take the infimum over all strategies. So this is the minimum probability, or we can take the supremum over all strategies, and this gives us the maximum probability of reaching the target over all strategies. So what I'll also use sometimes as for DTMCs is the vector of probabilities. So either the vector of minimum reachability probabilities or the vector of maximum reachability probabilities. So let's first look at 2 examples. So let's first look at this simple DTMC we saw earlier, and let's consider the probability that we reach the target set tails. So if we consider our strategy from before, sigma I, the first selects B for the first I -1 times and in state S1, and then select C. So sigma 1 select C the first time that it's in S1, so we go from S0 to S1, and then with probability 1/2 we end up in S3. On the other hand, if we consider the strategy that first chooses B, the first time in S1 and then always chooses C, well, we can see after that there's always probability 0.5 that it either goes to S2 or S3. So the probability of moving to of the target set tails being reached is again 0.5. Now, if we consider the minimum probability, well, we've got the strategy that always chooses B in state S1, and in this case, we'll either always take this loop here, or we'll move back to back to S0, then move to S1, then we'll choose B again, and we'll go back to S0 and then back to S1. So the minimum probability for this MDP is 0, while the maximum is 0.5. And there's a number of different strategies that achieve this, as we've seen. Both sigma 1 and sigma 2 achieve this, and in fact sigma n for any n will also give probability 0.5. Now let's consider a slightly modified MDP, where if we choose action B, there's still a probability 0.7 of going to S0, but now instead of the self loop, we now move to state S3, or our target, with probability 0.3. Now, if we consider sigma 1 in this case, we go to S1, and then there's a 0.5 probability of reaching S3. On the other hand, for sigma 2, if we first choose B, then we've got a probability 0.3, or we go back to S0, then the second time we take this transition C, and we've got, or this action C, and we've got a 50-50 chance. So it's 0.3 plus 0.7 times 0.5. For sigma 3, so we either have the 0.3 or we go back, and then so the second time we again choose B. So we then have 0.7 times 0.3, or we go back to S0, and then it's like the third time we choose C. So we have 0.7 times 0.7 times 0.5 in like the third case. So here, so the max, so the minimum is still 0.5, and that corresponds. Sorry, now it's like the minimum is 0.5 as opposed to 0, and here we just choose C. So the first time, and so the maximum is 0.1, and here so we always, this time if we always choose B, then so eventually we will always take this loop here, and we will end up in S/3, because it's like the probability of always taking this branch will be like 0. Okay, so that's an example. Now, it turns out that for reachability probabilities, we can just consider memoryless strategies. So these are strategies that always pick the same choice or same action in a state. So these are also known as positional, Markov, or Markovian, or simple strategies. And here we can just write them as a mapping to available actions. And then the induced DTMC can have the same state space as the original MDP. So just to give you one example, so from the previous example, if we consider the strategy sigma 1 that picks C in state S1, then the induced DTMC has the same state space as the MDP, and in state S1 we just have the transitions corresponding to the action C. So we go to S2 with probability 0.5, and we go to S3 with probability 0.5. So there are other classes of our strategies. So we've got finite memory strategy. So here there's a finite number of modes which can govern the choices that the strategy makes, and they can formally be defined by deterministic finite automaton. And the induced finite, the induced DTMC is now can be a finite MDP. So recall in the general case, the induced DTMC is infinite state, because the set of states corresponds to the set of all finite paths corresponding to the adversary in the MDP. We also have randomized strategies. So here it maps a finite path to a probability or distribution over the available actions, and these generalize the deterministic ones that I've introduced so far, and these will still induce a possibly infinite state or DTMC. And we also have the class of fair strategies, which impose fairness assumptions. For example, if an action is available infinitely often, then eventually that action will be chosen. So now I will go on to probabilistic reachability for MDPs, and I'll first consider the qualitative case of where the minimum or max, finding the set of states for which either the minimum or maximum reachability probability is greater than 0. Okay, so let's first consider. So we've got, so here, we want either the minimum probability from state S of reaching the target T is greater than 0, or the maximum probability of when starting from state S, we reach the target T is greater than 0. So for the max case, so this is the set of states for which the maximum probability is greater than 0. So this just corresponds to non-probabilistic reachability. So we start from our target set, and while we find new states, then we update our set of our states. So we find all states for which there is some action and some state in the reachability set we found so far, so that we can enter that state, and we keep doing this until our set does not change. This is just a standard of reachability. We start from the target, then we add in all states that can reach the target in one step, then all the states that can reach the target in 2, and so we keep going until our set of states does not change. Okay, so in the min case is very similar, but we require, under all possible non-deterministic choices, there is a transition into our current target set. So that's all that changes there. So let's now move on to the optimality equations for probabilistic reachability. So the values of the minimum probabilities can be are the unique solutions of the following sets of equations. So the minimum probability for state S. So if it's in the target, obviously it's 1. If P min is not greater than 0, therefore it's equal to 0, therefore we set it equal to 0, and otherwise it's defined recursively based on the successor states. So it's the minimum probability, so it's the minimum over the available actions, and this is just the probability that we move to state S prime if we choose action A in state S, and then the minimum probability from state S prime of getting to our target. So this is what is known as an instance of the Bellman equation, and it's the basis of dynamic programming techniques for MDPs. So for max, it's almost the same. All that we change is here. So the second case is the case where the maximum probability is equal to 0 as opposed to the minimum. And here we take the max over the available actions, while previously we took the minimum over the available actions. So as I said previously, memoryless strategies are actually sufficient for probabilistic reachability, and they are strategies that always pick the same choice in a state. And so just to be more precise, what I mean by sufficient are that there do exist memoryless strategies that achieve both the minimum probabilistic reachability values and the maximum probabilistic reachability values, and they can easily are constructed from the optimality equations. So you can just, after you've got the values, you can just find in each state which is the action that actually yields the minimum of value. So just to add at this point that memoryless strategies are not always sufficient. For example, although they are sufficient for reachability in turn-based games, we actually need finite memory strategies when we consider bounded properties. So here, why do we need it here? Well, for example, if we have if we want to reach a set of states, it's like within a certain number of steps, then if we've got a large number of steps left, then it might be best to choose a longer route that has a higher probability. But if we've only got a few steps left, then it might be better to choose a shorter route that has a lower probability. It's also needed for both LTL and automata-based properties. We also need randomized strategies for our concurrent games, and for reachability properties, they can be memoryless, but we need them to be randomized. On the other hand, we need both finite memory strategies and randomized strategies for multi-objective properties. Okay, so let's finally get onto computing reachability probabilities that I will cover in the final video.